Yeah, good morning, students. In the previous class, we were seeing about the uh, electric field intensity and electric field density. So now in this unit, we'll see about the magnetostatics and Maxwell's equation. So in this unit, we are going to see about the Biot Savart Law, Ampere circuit law, application circuit laws, and magnetic flux density, Maxwell's equation for static fields, Faraday's laws. In Faraday's laws, we will see about the transformer and motional EMF, displacement current, and Maxwell's equation in final form and time varying potentials. So in the previous unit, we discussed about the electric fields in which E represents the electric field intensity and D represents the electric field density. So in this unit, we'll see about the static magnetic field, which is characterized by H. H represents your magnetic field intensity and B represents your magnetic flux density. So how electric field intensity and electric field density is related is D is equal to epsilon into E. In the same way, the magnetic field intensity and the magnetic flux density is related by B is equal to mu into H. So here in this unit, there are two major laws governing the magnetostatic fields. One is the Biot Savart law, the other one is the Ampere circuit law. So like the Coulomb's law, which we have seen in the earlier unit, Biot Savart law is a general law of magnetostatics as like the gas law. So generally gas law is a special case of Coulomb's law and Ampere's law is a special case of Biot Savart law. So this is applied for symmetrical current distribution. So now let's see what is Biot Savart's law. So the law states that the differential magnetic field intensity dH produced at a point P due to a differential current element I dl is nothing but directly proportional to the product of the current I and the differential length dl and the sine of the angle between the element and the line joining the point P to the element, and it is inversely proportional to the square of the distance r between the point P and the element. So your Biot Savart law says that the differential magnetic field intensity is directly proportional to I dl sine alpha divided by r square. So we can consider this as a line in which the current flowing through the line is I. And in this line, we are going to take a small length, which is represented by dl. And the angle between your line and the angle between the line joining the point P and the element is defined by alpha, or else you can also have it as theta. So therefore, and the line joining the differential length and the point P is represented by the distance r. So we can write to exclude this proportionality sign, we can write it as dH is equal to K IDL sine theta or sine alpha divided by r square, where K represents the constant of proportionality, which is nothing but 1 by 4 pi. So instead of K, we can just write 1 by 4 pi. We can substitute in this equation. Therefore, you get dH is equal to IDL sine alpha divided by 4 pi r square. So we know from the definition of cross product, the differential length. So if you put an arrow mark in the above means it is called as the vector. So if you have a cross product between the differential length and the unit vector AR, we can write it as DL AR vector sine theta. So since the magnitude of the unit vector is equal to 1, we can write dl into sine theta. So therefore, in the place of, in the previous equation, in the place of I dl sine theta, we can write as dl into AR. So because we have arrived at dl into AR is equal to dl magnitude of the unit vector into sine theta, where the magnitude is equal to 1. Therefore, we have winded up with dl sine theta or sine alpha. So the same way it is over here, dl into sine alpha. So instead of this place dl sine alpha, we can also replace with dl cross product with the unit vector. So I've just replaced and written the equation again. So therefore dh is equal to I dl into AR unit vector divided by 4 pi r square. So again, this AR can also be written as its direction divided by its magnitude. And therefore, I can write this instead of the unit vector AR, I can also write it as R divided by magnitude of R. Already in the denominator, R square is there. Therefore, this R will come. Therefore, I have written it as R cube. So I can write the differential magnetic field intensity is equal to IDL R divided by 4 pi R cube. So the direction of DH can be determined by the right hand thumb rule. We all know that right hand thumb rule. So the right hand, so this is how you keep the right hand. So the right hand thumb is pointing in the direction of the current and the right hand fingers are encircling the wire in the direction of the DH. The same way, the same right hand rule is applicable over here. So here if you see the screw which is placed along the wire and pointed in the direction of the current flow and the direction of advance of the screw in the direction of the DH. So to represent the direction of the magnetic field intensity H or the current I, we use a small circle either with a dot or a cross sign. So inside the small circle, either you represent a dot or a cross like this. So depending on whether the H or the current, depending on the magnetic field intensity or the current is out or into the page, we can put the dot product or the cross product inside the small circle. So the dot represents the dot which is inside the small circle represents the magnetic field intensity or the current is out of the page. And if you put a cross inside the small circle, it represents the magnetic field intensity or the current is into that page. So different current distributions are there. We all know that one is line current, surface current, and the volume current. So here the K represents the surface current density in amperes per meter, and J represents the volume current density in amperes per meter square. So how we have written over here in this equation, where DH is equal to IDL. This is for a line current. That's why we have represented a small differential length. The same way we can also write it for the surface density and the volume density. So how can we write that? So IDL can be replaced by K into ds, which represents the surface current density, where K represents the surface current density and ds represents the differential surface. And it can also be written in terms of volume current density, representing it as J into dV. Therefore, when you write for the magnetic field intensity, previously the equation was differential magnetic field intensity. So if you remove the differential, here you have to put the integration. So H is equal to, if it is for line current, you have to put integration L IDL into AR divided by 4 pi R square. So this is for the line current. Similarly, for the surface current, we can replace the IDL into KDS. So H is equal to integral S KDS into AR divided by 4 pi R square, which represents the surface current. And similarly, for the volume current, the magnetic field intensity H can be represented as integral V JdV into AR divided by 4 pi R square. So to determine the field due to a freight, now we'll see an example for the Biot Savart Law. So how to determine the Biot Savart Law we can see. So to determine the field due to a straight current carrying filamentary conductor of finite length AB. Now let us see about this diagram. So you are considering a current carrying filamentary conductor. So this is your AB. So in this AB, you're going to take a differential length which is represented in DL. So this current carrying filamentary conductor is in the direction of Z axis. Now you try to draw a line. Now you try to take a point P in space. Okay, so I have put a small circle. Inside the small circle, I have put the cross. The meaning is the magnetic field intensity or the current is into the page. That's why we put a small circle and the cross inside. If we put a dot inside, the understanding is the magnetic field intensity or the current is out of the page. So you take a point P in space, and to that point P, what is the magnetic field intensity? That is what our intention to find. So here you have taken a long straight current carrying filamentary conductor where you have taken a finite length AB, and in that finite length you have taken a small differential length which is represented by dl, and you have taken a point P in space, and we need to find what is the magnetic field intensity at the point P. Now you try to draw a line from B to point P, and from the differential length center to the point P, and from A to point P. And then this will be your angle alpha, and this will be your angle alpha 1 and alpha 2. And the line joining the differential length point element and to the point P is the distance r. So assume the conductor is in the z-axis, that is what I have said, and the lower end subtending angles are alpha 2 and alpha 1 at the point P. Now we need to find what is the current distribution dH at the point P due to an element dl at 0, 0, z. How this 0, 0, z comes? Because your long straight current carrying filamentary line is in the z-axis, and it is nowhere related with the x or the y-axis. That's why we have put for x, y, z coordinates. X is equal to 0, y is equal to 0, and z is equal to z-axis only. You have the straight long filamentary current carrying element. So we can write dH is equal to IDL into R divided by 4 pi R cube. Now in this diagram, if you see, this is your z-axis where the finite length AB is there, and this is your alpha. That means this point will be your differential length, and this point will be your point P. And the line running from the differential length to the point P will be your distance R, and this will be the rho, that is the radius. So the unit vector along the rho will be the A rho, and the unit vector along the z-axis will be the AZ. Now we need to find what is dl. So what is dl? Dl lies in the z-axis only. The z-axis we have taken a small differential length, that only we have represented as dl. So dl is nothing but dz into az. Because it lies in the z-axis, we can write dl is equal to dz into az. Now what is r? You need to find this r. So how can you find this r? This minus this will give you the answer for r. So I can write rho into a rho unit vector minus z into az unit vector. Now we have this equation. In this equation, in the place of dl into r, you can also replace with dz into az. What is dl? Already we have said dz into az. What is r? We have defined over here. Rho a rho minus z az. So in this equation 1, in the place of dl into r, I'm going to replace the value of dl as dz into az, and I'm going to replace the value of r as rho a rho unit vector minus z az unit vector. So I've just replaced and kept, and then you have to multiply inside. The normal multiplication inside the brackets you have to do. So therefore dz az into rho into a rho minus dz az into z into az. That will be the multiplication if you multiply inside the brackets. So here the cross product between two different vectors will result in the third vector. The cross product of the same unit vectors will be equal to 0. We all know that the properties of cross product and the dot product. So the cross product between two vectors az and a rho will result in the third vector as a pi, and the cross product between same vectors az and az will result in the value of 0. So if this is 0, this value will get vanished. Therefore dl into dr will be rho dz into a pi. Now in the first equation, what you had in the first equation, just replace your dl into r by this third equation, that is rho dz into a pi. So when you replace, what you get, dh will be equal to I already, which is there in that first equation. In the place of dl into d rho, you are going to replace with this. So rho dz into a pi divided by 4 pi. Again in the place of r, I'm just going to, this is my r, I'm just going to replace with rho square plus z square. Already it's there is a cube is there, so I have written it as 3 by 2. Okay, so here we know that cot alpha is equal to z by rho. From this diagram we know that if we want to find the cot alpha, it will be z by rho. So I can cross multiply and get it. Z is equal to rho into cot alpha or theta. So for angle, if you are mentioning by alpha, continue the same from the beginning, or else you make it as theta. Okay, now you just differentiate with respect to alpha and z. Therefore, I'll get dz is equal to, in for cot alpha, the differentiation will be the minus cosecant square alpha. So I can write, so I'm just doing differentiation with respect to z and alpha. So I get for z, it is dz, and for cot alpha, it is minus cosecant square alpha. So this row will retain the same. Instead of cot alpha, I'll get minus cosecant square alpha into d alpha. So just replace these terms to this equation. So I'll get dh is equal to this 4 pi, I will take it outside, and this so I'll get 1 by 4 pi. This I will retain the same, this row will retain the same, and instead of dz, I'll just replace with minus of rho cosecant square alpha d alpha. So this minus will come over here when I replace for dz. So I'll get rho cosecant square alpha d alpha into a pi divided by, and in the denominator already 4 pi I have taken it outside, and therefore rho square plus z square is there. So rho square plus, instead of z square, I'll just replace with this. So rho square cot square alpha 3 by 2. Now what I have to do is, I can take I outside because it is the common term. So minus I by 4 pi integral alpha 1 to alpha 2. How this alpha 1 to alpha 2 comes? Because the finite length angle will be alpha 1 and alpha 2. So I've taken those as the limits. So since I've taken the I outside, I'll get rho square cosecant square alpha d alpha as it is, a pi divided by, in the denominator, rho square is a common term. So I'll take the rho square as a common term, 1 plus cot square alpha to the power of 3 by 2. So I'll be getting minus I by 4 pi integral alpha 1 to alpha 2. And then a rho square cosecant square alpha d alpha divided by rho square, this power term I have taken, so into 3 by 2, and for this term as it is I put 1 plus cot square alpha into 3 by 2. So when you cancel out these powers, you will be getting rho cube. So again in the numerator, this 2 and this 2 will get cancelled, 2 into 3 by 2, right? So this 2 and this 2 will be cancelled, therefore it will be rho cube. And the numerator rho square is there. So I'll get only 1 by rho. If it get cancelled, I'll get 1 by rho. So minus I divided by 4 pi, already it is outside the integral. Now here if I, after cancelling, I'll get 1 by rho, so that I have written. Therefore integral alpha 1 to alpha 2. The remaining terms will be cosecant square alpha d alpha divided by 1 plus cot square alpha is nothing but cosecant square alpha to the power of 3 by 2. Okay, now I'm trying to cancel out the numerator and the denominator. Therefore, I'll get minus I divided by 4 pi rho integral alpha 1 to alpha 2, 1 divided by cosecant alpha d alpha a pi. So therefore, this a pi unit vector is also a constant. So I'll take it outside the integral. Therefore, integral alpha 1 to alpha 2, 1 by cosecant alpha is nothing but the sine alpha d alpha. So for sine alpha, if you integrate it, means sine alpha is nothing but minus cos alpha. And I substitute the limits alpha 1 and alpha 2. Therefore, I'll get minus I divided by 4 pi rho. When I substitute the limits, I'll get minus cos alpha 2 minus of cos alpha 1 into a pi. Therefore, I'll get H is equal to, H is nothing but the magnetic field intensity at the point P will be equal to I divided by 4 pi rho cos alpha 2 minus cos alpha 1, because this minus I have taken outside, already one minus is there, therefore minus into minus plus will become, but this term will become cos alpha 2 minus cos alpha 1 a pi. So this is the equation for the magnetic field intensity H at the point P. So there are some special cases out there. What are those special cases is, so previous case we have taken a finite length. Now we'll try to take as a semi-infinite length with respect to point P. So semi-infinite length means I will take A will be an infinite point and B will be a finite point. So A I will take it as 0, 0, 0, and B point I will take it as 0, 0, alpha. So my angle will be alpha 1 will be equal to 90 degree and alpha 2 will be equal to 0 degree. Therefore, my magnetic substituting these alpha values in my magnetic field intensity equation, H is equal to I divided by 4 pi alpha rho cos alpha 2 minus cos alpha 1 a pi. So when I substitute the value of alpha 2 is equal to 0 degree and alpha 1 is equal to 90 degree, cos 0 will be equal to 1 and cos 90 will be equal to 0. So therefore, I'll get the magnetic field intensity H is equal to I divided by 4 pi rho a pi for the semi-infinite line. The same way we have another case is also there when the conductor is infinite in length, that both the points A and B is one is plus infinity, the other one is minus infinity. Then what will be your magnetic field? So the point A will be 0, 0, minus infinity and the point B will be 0, 0, infinity. Therefore, your alpha 1 will be equal to 180 degree and alpha 2 will be equal to 0 degree. So you just substitute this alpha 1 and alpha 2 values in the magnetic field intensity equation. So therefore, you'll get the answer H is equal to I divided by 2 pi rho A pi. So determine the A pi. We have a cross product of two different vectors will be equal to the third vector. So A pi can be written as AL into A rho. So AL will be the unit vector along the line current and A rho will be the unit vector along the perpendicular line from the line current to the field point.